Hello, welcome to Accurate Logic and Signal Power Estimation with Xilinx Power Estimator Quick Take. The major differentiator for Xilinx in 20 nm UltraScale families and now extended to UltraScale Plus is the routing architecture innovation to deal with the number one bottleneck to system performance and power for next generation designs. We redesigned the routing infrastructure with more flexible switching and doubled both horizontal and vertical routing resources relative to 7 series to minimize routing delays and support rapidly increasing logic density. Collectively, these core innovations are what enable devices built on the UltraScale architecture to deliver extremely high utilization while maintaining maximum performance. Accurate power estimation is very crucial as power is now the number one constraint for many designs. As device density grows, larger designs tend to hit heavy routing complexities and larger fanouts. Depending upon the amount of switching, it will expose more and more interconnect power. If we take a closer look at total power breakdown, logic and signal power alone can be somewhere between 40 to 70%. This eventually reveals that a special attention is needed on logic and signal power to achieve accurate total power estimation. The traditional approach is not good enough to gauge power dissipation in this next generation routing architecture. Though Xilinx Power Estimator is very abstract interface with minimal configuration settings, we constantly look for opportunities to improve accuracy of power estimation, which helps our customers with early design strategies and decisions. As we know, device dynamic power is purely depends on effective switching rate, which decides number of times the node capacitors are charging and discharging during operation. As a first step towards accurate logic power estimation, we redefined toggle rate specification for logic in XPE. Let's take an example of 4-input LUT for our study. If we take a closer look at major power components of LUT, there are 3 node capacitance in it. First one is the node capacitance of the logic itself. Second one is the input capacitance for each LUT input pins, and at last the output pin capacitance. The logic capacitance exists as long as it is powered on, whereas the power on input and output node capacitance are completely dependent on input and output toggle rates respectively. So we need both input and output toggle rate to accurately estimate logic power. There is no specific interface change in XPE. However, the toggle rate now represents average toggle rate of both input and output. You might have entered higher toggle rates in the past to represent switching activity at the output of pin LUT. Now you might have to slightly scale it since it is average of both input and output pins. It's always very challenging to group an average toggle rate in a clock domain because each node has different capacitance and there are different input LUTs, LUT1 to LUT6. Since Vivado report power has more accurate toggle rate and capacitance per node while importing to XPE, it uses weighted average toggle rate with respect to node capacitance for best representation to achieve best correlation results between these tools. Here comes the major change to address power estimation challenge with massive routing architecture. Let's take an example. We have a CLB with 2 active LUTs and a flop. This specific LUT drives various loads in the fabric. LUTs and registers in other CLB, BRAM and DSP at different regions. So it has 8 fanouts in this design. This is what you might have entered in the previous XPE interface, which worked perfectly well for small and medium scale devices and until all 7 series architectures. However, UltraScale fast-track routing and optimal packing use efficient routing techniques with variable wire lengths. The fanouts within CLB uses logic routing which doesn't contribute to external signal power, whereas the fanouts in different clock region will have different wire lengths. And also, the node capacitance at every horizontal or vertical interconnect track varies depending upon the choice of routing path. So we need to consider all these key factors to accurately estimate the signal power. We realized that we really need a holistic approach to handle heavier and complex routing structures in UltraScale and UltraScale Plus. We introduced a smart algorithm called routing complexity in XPE by replacing legacy fanout based logic specification. All the key factors influencing signal power are nicely wrapped in this approach based on physical implementation of routing complexity. More importantly, this new algorithm scales with the design, size and complexity level in both UltraScale and UltraScale Plus devices. When it comes to XPE interface, we carefully crafted the use model with one parameter change, introduced routing complexity column by replacing fanout setting. This represents the average number of routing resources per logic cell of logic groups in a row. For example, here 10k LUTs are grouped in a row, which means routing complexity of each LUT is 8. Literally, you can enter any valid integer numbers in it, since routing complexity is a simple factor to say whether the design uses average interconnect usage or can be shifted to be the above and below average. However, we have clear guidelines for early averaged estimations based on statistical analysis on various use case designs. Routing complexity need to be set as accurate as possible based on design size, average number of fanouts in the design, and most importantly, routing resource efficiency. The average value for routing using the routing complexity unit is 8, and that is what XPE default is set to. This would be the ideal value for most of the designs with highly pipeline logic and more controlled fanouts. Especially in larger devices maximum resource utilization, you can set it to 10. Not all designs fall under this. Very few larger wired communication designs tend to fall in this category. In the extreme cases like bigger devices with maximum resource utilization and complex routing, you can set it to 12. But this is highly unlikely for most of the designs. As you can see, this number could be guided up to 12 if above average routing is expected, or down to 8 if less than average routing is used. However, these factors have steep exponential relationship with total power. It is not recommended to go either extremely high or extremely low with numbers, as it's very rare to have designs as a whole that exceeds 12 or is below 5. In the imported results from Vivado report power, you might observe very high or very low routing complexity values, which exactly represents the complexity severity of specific logic in the implemented design. For example, the reset logic block can have higher values since it drives larger fanouts across the device. However, the toggle rates on those nets are very low and thus do not generally have a larger contribution on power, even though they have a high routing usage. Really, the toggle rate decides the amount of power burnt on those logic and signals. In a summary, power estimation using logical representation already hit its boundary. Massive routing architecture in UltraScale and UltraScale Plus requires smart algorithm to estimate accurate logic and signal power. Our latest XPE 15.4 or latest comes with all new algorithm, effective toggle rate specification for logic, and a single common parameter routing complexity is introduced to cover the key factors of signal power. What we have got is an impressive accuracy correlation of plus or minus 10% with respect to Vivado report power. Even though XPE is a very abstract level of interface with minimal configuration, Xilinx constantly looks for opportunities to improve accuracy and reliability of power numbers in XPE. What's next? Download XPE 15.4 or later to estimate your design power accurately much earlier in the design cycle. Contact Xilinx support and/or your local field team for more information. Thank you for watching the video.